Okay, so before we go to the complete derivation of basically LDO, we need to first understand the concept of output impedance in open loop and feedback, and then we'll move there. So so if this is our out and this is your GM. So let's say this is in the open loop, just like we have. So what will be the effective R out of this or output impedance? R out. Okay. So if this is voltage controlled current source, then you can assume the impedance looking at the current source is infinite. So your impedance will be defined by whatever is connected at the output of this GM block. So our output impedance is R out. Now, so this was your DC. So what is the AC output impedance? If this is C out, can anybody tell what is the AC output impedance, or if I want to call it Z out, what will be that? Hmm? Resistor in parallel with capacitor,
So R out by R out, C out, S plus 1. Yeah.
Okay. So which means what would happen at the higher frequency? Your output impedance will be reducing or increasing.
It will reduce.
No, vary. Obviously, it will vary, but vary.
It will reduce with
Reduce.
S, right? I mean, and it will reduce with higher frequency.
Yeah, it will be first order response, correct?
Yes.
So Z out, and this is nothing but your R out DC, and then you have a pole at 1 over R out C out. So that's why when you connect the large cap at the output, so and what I mean, ideally, what do we want for any supply? What should be the output impedance, low or high? What do we prefer?
Should be low, sir.
Yeah, should be low because we don't want any change in the output voltage when there is a change in the current. Okay, so that's your basically delta V out or delta I out ideally should be 0. So there should not be any change in the voltage because I want to keep it very stable, regulated. So your delta V out over delta I out should be 0, which means your R out should be 0. So as you increase the frequency, so at high frequency, obviously your capacitor will block any changes. So in the output, because it will act as a short circuit, and that's why you see your output impedance is increasing. But if you have any slow frequency change, then it will be determined by your basically R out. So let's say you have a DC change. So in the DC change, how much change in the voltage with respect to the change in the current will be determined by your R out. So smaller the R out, basically better your DC impedance would be, and that will give you basically better load regulation also. So remember the load regulation was nothing when you change your load current. but this load regulation we are defining with respect to a small signal, not a large signal. So your small signal load regulation will always be better if your output impedance is small. Okay, so now this was in open loop. Now let's say I connect in the same thing in the closed loop. GM R out. So, so let's say with some beta scaling factor, I am connecting this output to. So what will be the R out or I'll say closed loop actually. What will be
With
that?
approximation, it will be 1 by beta GM.
1 by beta GM. Beta GM, okay. So approximation is coming up because why? In with negative feedback. I'm just directly basically writing the expression, but you
High
can derive it.
frequency.
You can derive it. And in order to derive, what you need to do, apply a test, basically voltage source at the output, and V test over I test. That will be your output impedance. And in the closed loop, you can find that. And what you'll be getting actually approximately your R out closed loop will be R out over loop gain. Okay, and what is loop gain here? Is nothing but beta GM into R out. Correct. So now R out over beta GM into R out. This cancels out and you get 1 over beta GM. Which means whenever you connect your system in the negative feedback, your output impedance will be suppressed by your loop gain. So if you know the loop gain already, I mean, you are doing loop gain analysis, you know the loop gain transfer function. All you need to do in the open loop, whatever R out you are getting, just divide that by your loop gain and you will get that. So if you have a 2-stage, 3-stage, it doesn't matter in that case. Okay, so we looked into the first order impedance basically in the feedback, and what we saw that at DC it will be suppressed by your loop gain. So whatever the feedback gain you have, it will be suppressed by that. So DC will be like beta A naught, where A naught is beta A naught is nothing but your loop gain. So, and as you move at a higher frequency, since you have a pole at the output in the first order, so basically what will happen, your output impedance will further start dropping because you have a capacitor at the output, and that capacitor will basically cause the output impedance to further reduce at higher frequency. So now let's look at, so if we want to generalize, so in the, so your general is Z out, or let me write this, Z out S equal to Z out S when I say close loop equal to Z out, let's call it open loop S divided by 1 plus beta S. So whatever the output impedance you have in the open loop, that will be suppressed by your 1 plus beta AS, where beta AS is your loop gain response. And if you want to calculate the DC, then it will be nothing but 1 plus beta naught, and Z out open loop will become simply your R out. So R out divided by loop gain, we know that will be your DC impedance. So now for the second order, so here your AS is beta naught divided by 1 plus S over omega P1 into S1 plus. So where omega P1 is not P1, let me write it whatever we used earlier. We used omega P gate and omega P out. So let's keep the same names for poles so that we don't get confused. So omega P gate is 1 over R gate C gate 1 over R out C out. Beta is R2 over and A naught is GM1 R gate first stage multiplied by second stage, which is GM2 R out. Okay. So we'll just instead of writing like in detail, like in terms of GMRN, we'll just refer to omega P gate and omega P out so that your expression looks cleaner. So now we'll substitute here this guy AS in we'll substitute here your AS, and Z out is already known, which is R out. So let me write Z out as well. So Z out open loop is R out over 1 plus R out C out. So let's substitute both, and what is this 1 over R out C out? What is that in terms of omega if I want to write? This is same as omega P out, correct? From here. So we'll substitute this, and we'll find the transfer function for Z as closed loop, and that becomes your R out divided by 1 plus S over omega P out divided by 1 plus beta and A naught divided by 1 plus S over omega P gate into 1 plus S omega P out. Okay. So this goes away, and what you have here is R out Okay, so if I want to do the Bode plot for this, so how many poles and zeros you have here? Can anybody tell how many poles and zeros?
2 poles and
1 0 and 2 complex poles.
How can you say it's a complex pole, huh? Why do you say complex pole? I don't understand. Where is the complex term here?
I mean second order.
Yeah, second order could be anything, huh? Second order is not always complex. Okay, so it's a second order system. You have 1 0 and 2 poles. So if let's say I'm only interested in doing the Bode plot, what is the separation between the, I mean, after compensation, what is the separation between the 2 poles? Can anybody tell? Omega P gate and omega P out. Let's say, I mean, ultimately, all these analysis needs to be done after compensation. Before compensation, I mean, calculating a Z out basically has no significance because your regulator itself will be unstable. So in that case, output impedance has no significance. So after you have compensated well your regulator with a, let's say, 60 degrees phase margin or higher, and then after that you are trying to see what will be the R out. So what will be the separation between omega P gate and omega P out after compensation? Can anybody tell? Roughly, what will be, what kind of separation you will have? In terms of beta and naught, what is that?
yeah.
Beta and naught multiplied by square root.
Multiplied by root.
Yeah, so beta and naught multiplied by square root 3 because beta and naught is your UGB and you want to keep your second pole, non-dominant pole, square root 3 times higher. So beta and naught square root 3 will be your separation between the two. Okay, so can I say that when I'm interested only within UGB, which one will be dominant? So let's say, so first you need to consider what compensation you have. So case one, omega P gate is dominant and omega P out is outside omega UGB. Okay. So which one will be dominant? Which terms? In the denominator, you have two S terms. Out of these, which one will be dominant inside UGB? Hmm? Omega P out term or omega P gate term? Which one will be dominant?
Omega P gate.
Yeah. So omega P gate is dominant. So can I ignore the second term? Can I say that that will be like non-dominant and we are only interested inside omega UGB? So the second pole will have no impact within UGB, correct? So that approximation we can make. So for omega less than omega UGB, we can ignore omega P out. So this implies your Z out closed loop S is R out 1 plus S over omega P gate divided by 1 plus S over omega P gate plus beta naught. Okay, so I just removed 1 plus S over omega P out term. And what you have? Now the second order system has basically second order system converted into a first order system. So now R out divided by 1 plus beta I naught into sorry. Okay. So where is the pole and where is the zero? By the way, what is this? Can anybody tell 1 plus beta I naught omega p gate? What is this?
UGB, sir.
Yeah. So R out over 1 plus okay. So what you have actually, the pole, the dominant pole has basically got converted into a zero here, and your pole has shifted to UGB in the closed loop. And if you remember the DC gain in the feedback, that is not affected, and that you can look here. So this guy R out over 1 plus beta I naught, that remains same whether you have a first order or second order. It doesn't matter. So depending upon first or second order, all will matter is your high frequency response. And now it has changed. So in the first order, what was happening? You had a flat, which was R out over 1 plus beta I naught. And after that, it was dropping at higher frequency because it was only a single pole system and the pole was appearing at the output of your LDO. Now in the second order system, your dominant pole is at gate of your PMOS, basically PMOS, not at the output, and that's what's causing a zero here. So if I want to plot this impedance, so let's do the Bode plot. Okay, Z out, close loop, S. So I'm plotting the magnitude of this. So let me use different color. So this is your omega P gate. So what will be this flat gain? Can anybody tell this flat gain?
R out by 1 plus beta is it.
Beta naught, okay. And then what will happen? It will increase or decrease?
Increase, sir.
To increase.
Yeah, because you have a zero. And so it will go like this. And then you have your pole. Okay. So this is your omega UGB. Where is the non-dominant pole? That is, let's say square root 3 times. Or let me just write omega P out. So what will happen after omega P out? What will be the shape of this curve? What will happen after omega P out?
Down.
It will start coming down. Okay. Okay. So what does it mean? What is happening here? And what will be the maximum value of this? Can somebody tell the maximum value of this? The peak. Let me just move this guy slightly up. I will call it closed loop. What will be this value?
So,
Can I tell?
R out by 2.
Why are out by 2?
In the denominator, we have omega UGB. Say it omega is equal to omega UGB. Our denominator will become 2 times 1 plus beta A naught.
No. But you have to look in terms of magnitude. Huh? You cannot just directly substitute that.
Okay.
It will be square root by 2. Huh? How do you write a magnitude of
Yes,
transfer
sorry.
function?
Sorry.
Correct. That's why you have a 3 dB. Okay. So square root by 2. So you can say, okay, I mean, r out by square root 2. But let's say, so at that is at omega UGB. And when you say r out by square root 2, that is not the Bode approximation, but that will be the actual magnitude. So with the Bode approximation, can I roughly tell it is equal to r out? Okay, even if you take the real, I mean, you will have a roll off here, okay, around omega UGB. But at higher frequency, what will happen? It will hit the peak. So what is the peak value? That's what I'm asking. Can we tell the peak value?
That will be R out.
Yeah, that will be R out. Okay. Now go back to your circuit. So let's say I make this terminal ground. Okay. What will be the output impedance? Let's say gate of PMOS connected to 0 ground. So what will be the output impedance in that case? Hmm? Assuming that your effective output resistance is R out and capacitor is C out. That will be similar to what you have in the first order. Okay. So your feedback has no role after your UGB, which means you can assume that this feedback is completely broken because there is no gain as such in the feedback. So now if you connect this gate to ground, which means your feedback is not responding, your output impedance will be nothing but R out over 1 plus S over omega P out, and that's what is happening here at high frequency. And because the DC impedance at when you are looking at the output without feedback is R out, and that's why you are going towards open loop actually. So from closed loop, you started with a closed loop. Ultimately, around UGB, it will be start behaving like like an open loop system, and that's why you go back to your R out, and then after that you get a second pole which is at the output that will cause another basically roll off minus 20 dB per decade, and that's what you see the decay in the R out again. So now let's say I swap the pole. So now we'll take the case 2 where omega, okay, case 2, Okay, so let's take this expression again, this guy. So in this case, which one should be ignored? Can we tell which one will be ignored here?
Omega p gate.
Omega p gate. Okay. So which means 0 and pole both will go away. So what you have? R out over 1 plus S over omega and then again you have so let me copy this so that we can plot on the same graph. Copy, paste. We'll change the color. So it will start from here. And where will it go? Where is the pole? Can we tell the pole in this case 2?
Sir, at omega UGB.
Yeah. So you get a pole here, and after that, it will do like this. So this is your case 2, and this is your case 1. And this one, the second case looks, by the way, is this correct? What I plotted? Sorry?
The omega p, the omega p gate is non-dominant, so there the blue curve will be different. I mean, we have not considered that.
Sorry. You mean after UGB?
Yes, yes, after UGB. Right.
So after UGB, what do you have? You have both poles and 0, huh?
Right. Yes.
So why it will be different? So let's say I am looking at an open loop response, correct? Go
Okay.
back to the open. Okay. In the open loop, where will you start from? In the open loop, what will be the flat impedance, the DC impedance?
Routes.
Route. Okay. So and then at UGB, what will happen to Route? Think you have a minus 20 dB per decade. So at UGB, how much separation you will get at Route? Think about open loop. Don't even consider the feedback. I'm asking how much the separation you will get in the Route. So Route divided by how much? I mean, UGB is how much? 1 plus beta I naught times of omega p gate, correct? So if you have a first order roll off at UGB, your R out will be nothing but R out divided by loop gain. And that's what you have written here, R out over 1 plus beta I naught in the closed loop, correct? So which means the closed loop and open loop will intersect at what point? Will intersect at UGB, correct? And after UGB, your system is behaving like an open loop. So that means your closed loop impedance response and open loop impedance response will coincide with each other after omega UGB. So there is no effect of zero here. You have only pole. Correct? Any confusion in this? Okay, but in the other case, when you make your sorry, not omega p gate. In the case 2, I was talking about omega p out. When omega p out is dominant, then basically in the open loop, what will happen? You'll be starting with R out at omega p out. So let me just. So in order to avoid any confusion, let me write omega p out and this becomes omega p gate. Okay. So for case 1, your omega p gate is dominant, and for the case 2, your omega p out is dominant. So for omega p, when omega p out is dominant, you will be starting with R out in the open loop, and it will basically intersect at omega UGB, because at omega UGB, your basically loop gain will have the feedback gain will be unity. So they will intersect with each other, and after that, there is no feedback as such beyond UGB, because you have no gain in your basically your loop gain is less than 1 after UGB. So all the separation in the impedance will be coming from your output cap, and then you will have the same response what you had in the first order, which is basically it will follow the curve R out over 1 plus S over omega P out. And if you look at your closed loop response, that is also same, because after omega UGB, it will be falling with the same first order basically response, and they will coincide with each other. So there is no effect of zero as such when you make output pole dominant. So which one is better, case 1 or case 2? If you're designing a regulator, which one do you consider the basically better response in terms of performance, case 1 or case 2?
It's case 2, as R out is inherently lower.
Yeah. So for any regulator, when you are designing, you want to keep the output impedance as low as possible throughout the entire range of frequency. I mean, so one case, okay, obviously in the DC, if you look at DC impedance is same, and DC impedance basically will help you in when output impedance, nothing but your load regulation. So when you change the load current, basically you change the load current in terms of DC, then your output will remain pretty much constant because your R out is very small. But when you move at the higher frequency, then you are looking actually at the low transient response. So for the low transient, high frequency impedance matters. So which means at high frequency, if your uh, basically impedance is high, the output impedance, then it will degrade your uh, uh, low transient response. And this is clearly visible from here. You can see here, if you have a fast response, then around omega UGB, your output impedance is as high as R out. So then you will have a large dip. While on the other case, the case 2, your output impedance is, already suppressed by the loop gain, and beyond UGB you further get a suppression, so at high frequency. So here you will get a benefit beyond omega P out, and beyond omega P out also you have to travel this much in order to get back the R out by omega P out. So in this frequency range, from omega P gate until this point, your responses will not be good actually, because of this bump in your output impedance in case 1. So we can say that for better load transient, or let me write the way. So for P out dominant load transient better compared to when omega P gate is dominant. Okay, so that's the one thing you always need to remember. We talked about the output capacitor. You need a very large output cap, but that will always come at the benefit of your better transient response. Even though if your UGB is small, I already discussed that, because your output capacitor causes a reduction in the output impedance, so your undershoot will improve when you start increasing, because in beyond UGB, in any case, your loop will not help much in improving the transient response. But if you have output pole dominant, then even beyond UGB, that output capacitor will help in improving your transient response.